Okay, welcome again to today's webinar presentation. As you can see on my screen, today's presenter is Christoph Grebner, who is a senior scientist at AstraZeneca, and he will be talking today about the exploration and mining of large virtual chemical spaces. And since you cannot see us, but only the slides, here at least you can see a picture of today's presenter. And let me continue. With just a few guidelines for this webinar today. So by default, you are all muted so that we have the least amount of noise on the line. If you have any questions, please type them in. I am going to handle all your questions and hand them over to our speaker. And so you can do that throughout the webinar, but also in the Q&A session afterwards. Also, you won't have to take frantically notes during the presentation, but we will make a video recording available after the webinar on our webpage, so that you can take another look if interested or if needed. Oops, something is wrong with my presentation. Let me say a few words about today's speaker. Dr. Christoph Grebner obtained his PhD at the University of Würzburg in Professor Bernd Engel's lab. That was in 2013. Then a year later, he started as a system analyst for high performance computing at a company called GNS Systems here in Germany. Then 2015, he obviously thought that he wants to go back into science a little more and did a postdoc, and this was roughly speaking about modeling of the dynamic nature of proteins, and this was his first contact also with AstraZeneca, because this postdoc was partly with AstraZeneca and partly with the Barcelona Supercomputing Center in Spain. And afterwards, 2016, he started as senior scientist in computational chemistry in AstraZeneca in Sweden. And after having introduced Christoph, let me say a few words about myself. I'm Christian Lemmen, CEO of Biosolve IT. I'm very happy to have Christoph present today here in our monthly webinar series. And now that you know about us, it would be nice if you are willing to say a little bit about yourself. So for that purpose, I start a poll that should appear on your screen now. So if you could give us some insight about our audience, that will help us to tailor the presentation, and for my part also the moderation of the session better. And also it is nice to have an understanding about the background of the audience. Okay, 80% have voted already. That's very nice. Maybe a few more can click. Then we have a very good overview. And with that, I'm closing the poll in 5, 4, 3, 2, 1. Now, thanks a lot. You can see the result of the poll. So the vast majority, 60% roughly, are computational chemists, but also a second large fraction medicinal and bench chemists signed up, and nice to see also a few biologists and managers, decision makers here on board. So, welcome again to all of you, and that should also be the last step in my little presentation. So now I hand over the microphone to Christoph to give us his seminar. I must stop the poll. So, Christoph, now you have the microphone and also the screen.
Okay, thanks a lot, Christian, for this introduction, and I hope you can all see my slides now.
No, wait a second, Christoph. I think you still have to activate the U share, the screen. Oh, okay.
So, can you see it now?
Yes. Everything is good, but it's not in presentation mode. Oh, wait a second. It's not. Now it's in presentation mode. Okay.
Maybe not that quick, so we will see. Okay, so thanks a lot for the introduction, and I'm very happy to give my presentation about exploration and mining of large virtual chemical spaces here in this webinar. And when thinking about large or about virtual chemical spaces, I came across a quote from the Hitchhiker's Guide to the Galaxy. And this quote says that the space, in my sense, the chemical space is big, really big. You just won't believe how vastly, hugely, mind-boggling big it is. And in fact, if you look at the numbers, there are around 10 to the 11 stars in the Milky Way, or roughly 10 to the 23 stars in the observable universe. But these apparently very large numbers appear rather small in the theoretical number of molecules, which is estimated to be around 10 to the 60 molecules. And in that sense, if you want to search for similar molecules in a chemical space, this is quite similar than searching for similar stars in the universe. So this would, for example, be one of the query molecules. Our main goal or our task is to find all similar molecules or a set of similar molecules inside of this large chemical space. So with this in summary, our goal is to extend the searchable space beyond current limitations using different kind of algorithms and make it accessible to virtual screening methods to, in the end, find suitable molecules or select them for synthesis or test in projects. To give a short outline of my talk, I want to first discuss the virtual chemical space I'm using in this project. So it's mainly the AstraZeneca virtual chemical space. And afterwards, I will discuss how we can actually screen this space and how to build the space for being usable with different kinds of methods. And in the end, show some results about the so-called enumerated or fragment space searches, but more around these topics later in the talk. So as said, the theoretical possible space is around 10 to the 60 molecules. Obviously, only a small fraction of these molecules already exists. So in the yellow box or the yellow circle on the left, we can see that around 10 to the 8 molecules are real existing molecules. These are usually stored in databases, such like Campbell or similar kind of databases. And this also, of course, includes corporate databases, just like our AZ compound collections, which is around 10 to the 6 molecules. And if we now use information from our corporate database, we can extrapolate to the so-called AZ virtual chemical space, which is obviously overlapping partially with real existing molecules. And in the end, this space can encode to around 10 to the 15 molecules. And some key features of this space is that it's a quite diverse space, providing more than 4,000 different libraries. It's synthesizable in a way that we use historic AZ reactions, which we already know were working in library settings. And it's also searchable in either enumerated subsets or different ways, which I will discuss in this talk. And as an example of how to build the space, you can see a scheme here. So first we start from original reagents, which are pre-processed and clipped to give a set of building blocks like the one in the middle. And together with defined scaffold and suitable linker positions, we can generate a virtual molecule. For example, in this set, we can enumerate up to 4.5 or 4.6 million virtual possible molecules. And at the same time, we still keep the synthesizability as we only use rather well-established reaction rules. So as we now have a definition of the space, we also want to know how we can actually search this large chemical space. A general scheme how you could search a space is presented here. As said, we start with a complete space of around 10 to the 15 molecules. And in the end, we want to come out with a selection of suitable molecules, which we could then propose either synthesis or other virtual screening methods, and to select the nice or the best molecules. And in a way, we currently use two options to search our chemical space. In the first one, we enumerate a representative subset of the space and explicitly screen this space with a 3D shape similarity search. In detail, we use the FastROCS method. And this gives now a set of hits, which are somewhere located in the complete chemical space, which is illustrated by the picture in the middle, the small black dots in the complete chemical space. In a different option, we can also use the feature tree approach and to directly search the full space. And the results are in principle the same. We get a set of virtual molecules in the space. The workup of these hits is then completely the same. We first expand the hits via virtual synthesis and then rescore them with more advanced method, including both ligand-based and structure-based methods, specifically also docking methods, for example. And the compounds which score well in several methods, like in a consensus scoring approach, are selected for further synthesis. However, in this talk, I want to mainly concentrate on the primary search methods, which are the FastROCS and the feature tree method. To start with the FastROCS approach, which is a 3D similarity search method. The method itself is based on ROCS, which is the rapid overlay of chemical structures and is developed and provided by the OpenEye company. And it is a shape-based superposition method, which basically means that molecules are aligned based on the volume defined by Gaussian functions. And in principle, the more similar the molecules in shape in electrostatics, the more similar are the molecules. And thus, the assumption that the more similar the activity of these molecules is, like it is illustrated in the picture on the right. And FastROCS itself is now the GPU implementation of ROCS, which is capable of doing more than 1 million overlays per second and per GPU, which previously around only 1,000 overlays per second and per CPU with just using plain ROCS. If we want to search databases with methods like FastROCS or ROCS, we have to do some initial steps. So firstly, we of course have to use a database of pre-enumerated compounds. And also, we need to generate 3D conformers for this sets and basically also have to store these databases. And here, the size of the databases greatly defines the search time. So if I increase the number of molecules or the number of conformers per molecule, I also increase the search time. And the enumeration of a representative subset basically defines the search quality and the diversity. So which means it's pretty important to enumerate a good representative subset of the library. And the basic principle you could follow here is to enumerate as much as possible and searchable in a reasonable time. As part of the project, we're exploring different methods for virtual screening. We also wanted to see where the limits are for generating and searching pre-enumerated spaces. And for this, we developed in cooperation to the OpenAI company, a cloud-based FastROCS platform, which is running completely on AWS using the Orion platform of OpenAI. And the first step, obviously, is the enumeration of molecules, which is simply smiles sets in this context. And this already takes significant time when we want to enumerate 10 to the 9 or 10 to the 10 molecules, which is already 10 billion molecules, so a rather large number. But still, this can be considered a relatively quick task if you would compare it to the generation of conformers, which is the second required step. And because if we start enumerating 10 to the 10 molecules, we can see that this is a clearly time limiting and a very expensive step. So generating 10 conformers per molecule for 10 to the 10 molecules already required 55 hours on around 29,000 CPUs. And of course, you also need to store these databases, so including temporary files. This is a couple of terabytes. Importantly, this step is only needs to be done once, so you can reuse this database as often as you like. And in comparison to this, searching the large databases is now a pretty quick task. So we could search all these databases using 50 to 85 GPUs within around half an hour. The largest database, 10 to the 10, so 12 billion molecules, needs to be screened in 2 iterations, as we only got 85 GPUs in one go at AWS. However, when using 170 GPUs, I'm pretty confident that the timings would be quite similar, as it's scaling really nicely or linearly with the number of GPUs. As a second part of the project, we also want to learn more about the HZ virtual chemical space itself. Therefore, we generated different subsets ranging from 10 to the 5 to 10 to the 10 virtual molecules and searched them with 10 different queries and averaged the results, which you can see on this slide. As expected, we need more and more hits when increasing the search space to get a similar value or a similar set of hits. Here in this project, I used the threshold of the minimum 10 motor combo, which is the similarity measurement in the ROCS method, to be the same as the lowest values in the largest space. So basically, all results are relative to the minimum Tanimoto at the 200,000 hits in the 10 to the 10 space. However, very nicely, the maximum Tanimoto combo increases with an increasing space, which basically means we always find more similar compounds when going to larger spaces. So some outliers, like the black curve, the 2 black points in the 10 to the 5 or 10 to the 6 space, clearly depend on the nature of randomly enumerating molecules. And as these spaces are still pretty small, there's a higher probability that you enumerate a molecule which is not included in the other one, but still can be more similar to the query molecule. The most important result for us is on the left plot, on the left side of the plot, which shows the diversity, which is correlating to the number of scaffold. And this diversity seems to converge when going to 10 to the 9 or 10 to the 10 molecules. And this means for us that in our space, it is now more useful to increase the diversity instead of scaling up the enumerated space. Anyhow, if we look at these results and look at 10 to the 10 molecule and compare it to the full space of 10 to the 15 molecules, we can say, although this is an extremely large number to search explicitly, this is still a very low sampling rate of the whole space, basically only 0.001%. And therefore, we also wanted to explore alternative approaches which were capable of searching the full space. In the first instance, we explored the capabilities of the feature tree algorithm, which is provided by Biosolve-IT. And the principle of feature trees can be seen here. A query molecule is represented by a set of spheres, of features, and each sphere represents a profile of features. So in the small boxes, you can see that you have different features like donors, acceptors, amide-like or aromatic or hydrophilic. And then the different spheres or feature profiles are connected to give a feature tree of the molecule. The same is done with every virtual or non-virtual molecule, which you want to compare to a query molecule. In the next step, we now can map the different features from the query molecule to the virtual hit molecule to give an overall similarity score. In this example, this could give a similarity of 0.81 with a feature tree descriptor. And even nicer, we can also split the similarity into all different features to see which are more or less similar, to give medicinal chemists or project chemists a mean of what part of the molecule might be more interesting, or also value which molecules do I want to follow up in later stages. Another nice feature of this method is the feature trees is capable of doing scaffold hopping, which can be seen from this plot here, while the first hit is still very similar to the query structure on rank 1 with a feature tree similarity of 0.979. Already the 22nd ranked structure with a similarity of 0.899 shows a rather different structure. So although it still shows the same features of the molecule, it's a completely novel chemical series or a novel chemical molecule, which can give access to alternative hit series. So far, so good. So now we know how to use feature trees and how the ACID space is defined. But in contrast to the pre-enumeration methods like FastROCS, we need to prepare the space in a certain way that it is compatible with the feature trees, and then we can use it. The general search strategy of the feature tree method is shown here. We are starting with chemistry knowledge, which in a sense are our around 4,000 different reaction definitions. And this space is then pre-processed, and all reagents are pre-processed to give the chemistry space, which is encoding billions or trillions of compounds. This space is then searched with a query to give different hit molecules. And the nice feature, or the nice part around these different result hits, that these can still be tracked back to the original reactions and reagents. And it's pretty easy to find out which reactions were used to make this molecule and give back the information to the chemist to actually make a molecule. For pre-processing the space, you need to follow a couple of steps. We start with a scheme of the reaction, which is illustrated here. You have a building block on the left, you have several reagents which you want to use in the reaction, and you have a final product, which you give one example. The first step is to identify and extract the core and identify link atoms and replace them by unified linker atoms. Here they are called L1, L4, and L6. And afterwards, all reagents are clipped as well, and linker atoms are attached. And now you make sure that, for example, the reagents from L1 are used for the linker atom L2, and so on. These clipped reagents are stored in a unified reaction list, or unified list of reagents, and can be used for all different scaffolds as well. And in the end, to make it most efficient, you maintain a link atom compatibility matrix, which is defining which of the link atoms can be combined with which reagent atoms, like it's illustrated on the right here. Using these methods, we generated a set of different spaces. Obviously, I first concentrated on using the definitions of the ACID space. And for example, in the first space, using only reagents from one side of AstraZeneca I could build a space which is encoding to around 10 to the 14 molecules. Restricting this to only available reagents, of course, reduces the space to 10 to the 12 reagents, but at the same time gives access to a quicker synthesis, as the chemist can directly order the compounds or the reagents and make the compound. If you want to use all reagents at AstraZeneca, or for example, all enamine reagents in one go, this gives spaces of around 10 to the 16 molecules. And you can even combine the AZ and enamine reagents, which encodes to 10 to the 17 molecules, so it's giving one order of magnitude in addition. And this clearly shows that there are several reagents in both groups which are not overlapping, so it can be pretty interesting or pretty useful to use different reagent lists to search for similar molecules, to search for new or novel molecules. Of course, we can also use our reagents with the knowledge space from Biosolver-T to build a space. This, for example, with available reagents encoded to around 10 to the 13 molecules. So far, we defined how the space is actually built and how we can make molecules out of it. But where do we actually use the feature tree algorithm itself? So obviously, the scaffold can be represented as a feature tree, and likewise, we can also represent the building block as a feature tree. And as the features are completely additive, we can simply put them together to give a larger feature tree for the full molecule. Or here we still have one link atom left, which basically means we can iteratively build up a molecule based or starting from a scaffold and different reagents. This approach is called feature trees fragment assembly. And this now allows us to search the entire space without the need to enumerating one single molecule. So if you have a query molecule, like on the top left, you have a definition of the virtual chemical space, you can iteratively map different reagents and scaffold towards your query and find out molecules which fit to your query molecule. So now we also want to use or take these different spaces to compare results which we can get when we either use an enumerated set or enumerated space using different methods, or if we use a fragment space search. And we also want to know if there are any advantages or differences in the results we can get from these. As a first experiment or test, I tried to find a random query from the AZ space in an enumerated subset with 10 to the 8 molecules and in the full space with 10 to the 15 molecules. For simplicity, as we already had all the databases up and running, I used FastROCS for searching in the 10 to the 8 space and feature trees in the complete space. And I started with two subsets, which are the set 1 and 2. And these are built by randomly enumerating query molecules from the complete space with 4,100 reactions, but also making sure that only one molecule per reaction is used. In this result for set 1 and 2, we can clearly see that feature trees is capable of always finding the query in more than 96% of the cases. Basically, nearly all cases we can find the query in the space. FastROCS, however, only found the query in around 60% of the cases. This is rather surprising why FastROCS would not be able to find the molecules, but the reason is rather clear. So to explore this, I created two additional sets. The one set was created with only reactions having 2 or 4 linker atoms, and this represents the largest part of our virtual library, encoding more than 99% of all virtual molecules. And therefore, there's a pretty high chance that the query is not enumerated in the 10 to the 8 space. On the other side, I used set 4, which is using only reactions with 1 linker atom. This space is completely enumerated in the FastROCS library. As you can see from the results, that now if you use set 4, also FastROCS is capable of finding nearly all queries. And some queries are still not found, but this can be due to the fact that some molecules might be excluded from the database, either due to property restrictions, or that the conformer generation simply fails, so the molecule would be not included in the 10 to the 8. Looking at these results, we can summarize or conclude that FastROCS is capable of finding the query like it is with feature trees, but only if it, obviously, if it is in the search space, as you can see with set 3 or 4. And the key feature here is that as we only look at 10 to the 8 randomly enumerated molecules from this AZ space, this only represents a very, very small fraction of the AZ space, and there's a pretty high probability that key molecules are simply not enumerated. With feature trees, however, we always find the query, so we actually don't need to care about if the molecule is in a subset or not, but it's always included in the search results. Taking this information, the second question we wanted to explore is how diverse are the results coming from either a FastROCS search in 10 to the 8 or different other searches. Therefore, we here look at the results from 9 different queries, and we got 5,000 hits per query, and the overall results are obviously averaged over all the methods. And I compared 3 different methods. The first is FastROCS in the pre-enumerated set of 10 to the 8 molecules. The second one is feature trees in the full space. And on the last column, I also compared feature trees on the same sub-virtual library, 10 to the 8 molecules, as was used in FastROCS. We can clearly see that we get roughly the same number of unique hits. So basically, we remove all duplicates, which can come from different reactions, for example. And then all 3 methods find a similar rate of hits. However, it seems that FastROCS gives more different scaffolds. But likewise, we can see that also feature trees in the enumerated space gives more unique scaffold or more different scaffolds. So there can be several reasons why the feature tree in the fragment space only finds a lower number of scaffolds. One can be that as soon as you find a reaction or a scaffold which produces similar molecules, you will start to enumerate or start finding more molecules from this specific set. This means that if you want to explore the complete set, we either need to use more hits, which is in line with the results for the FastROCS searches, comparing for different sized spaces, or we can artificially limit the fragment search to a certain number of hits per scaffold. And if you find an interesting scaffold, we can always go back to that one and search it in more detail. In addition, if we look at the number of unique hits, we can clearly see that the FastROCS and the feature tree method seem to be quite orthogonal, as we only find hits in one method which are not found in the other method. And interestingly, also the scaffolds itself are quite unique. So even if we only find like 88 scaffolds on average with the feature tree in full space, 60% of those were not found with the FastROCS method at all. So this method clearly produces orthogonal results. But maybe more important in the end is the question if I by any means find good molecules with any of the methods. As I were quite limited in the sense of making molecules, so I couldn't just make all the virtual molecules we find here, I used the glide method from Schrödinger to judge if a molecule is good. So if it's producing well-docking molecules or a rather low or good score in the glide method, I would judge that this method produces a good molecule. And as you can see from the table, all approaches found comparably good molecules. Sometimes the one method performs better than the others, but in general, all results are very comparable and basically the same. It is also very interesting to see that feature tree is able to locate molecules with very good ROCS scores, for example, for project 1, but also ROCS is able to find molecules with a rather good feature tree score. And importantly, the fragment space often delivered a molecule which was not included in the pre-enumerated sets, so it couldn't be found with FastROCS or feature trees in the subspace. And sometimes these molecules even scored better, so it clearly adds a value searching the full space with the feature tree method. If we now look at all results together and judge are there any advantages or disadvantages when searching an enumerated or a fragment space search? We can see that the enumerated space clearly has the advantage that we can use a 3D search, which obviously gives more information or more connections to the bioactive conformations of the molecule. And also each single molecule can be explicitly searched and compared, also using more advanced methods, for example. However, the searches can be computationally expensive, depending on what methods you use. And the preparation of the databases and storing these results or storing the databases is clearly quite expensive if you look at the searches to 10 to the 10 in FastROCS. On the other hand, using a fragment space search, the whole space can be searched directly, which is not possible with any other method so far, and the searches are still very quick. For example, a feature tree search using the full space can still be done in a couple of minutes on a normal computer. As a clear disadvantage of the approach so far is that we are limited to a 2D descriptor, which is the feature tree descriptor, and all the spaces need to be built up by a reaction-based definitions. So we have to somehow define the space before we can use it. So ideally, it might be a good idea to implement a combination of fragment space search using 3D similarity to cover advantages from both worlds, or an alternative approach could be to initially search the full space with feature trees and take as much hits as possible, and then afterwards refine it with the ROCS method. At the end, I want to quickly note that we can also make the compounds we find in our virtual library. So over the last year, we used it in several projects, and we can see that the average delivery time for the first compounds comes to a time of roughly 3 months. And on average, we were also able to make around 70% of the molecules. And one should also keep in mind that we are not only using reactions with just one reaction center, but also more complex reactions with up to 3 or 4 linker atoms or reaction centers. With this, I want to summarize my talk about virtual screening and virtual chemical spaces. I showed you that we can search the whole AstraZeneca space by either using feature trees to screen it directly in a complete search, or we use our platform, which is able to enumerate and search billions of compounds with 3D and FastROCS. And as we see that feature trees and ROCS complement each other, it's a good approach to go forward and use these methods combined in projects. We can propose novel molecules, and we make them, and we also find novel hits with a shortening delivery time within around 3 months, and also several novel active molecules in a bunch of different projects. As an outlook for the future, we clearly want to apply our techniques in more projects and impact the synthesis or design of novel molecules, but we also want to extend the chemical space by either using more novel reagents or diverse building blocks, and explore alternative search algorithms for either chemical space exploration, like for example genetic algorithms, or deep learning algorithms to mine the whole chemical space directly. With this, I want to thank my co-workers at AstraZeneca, specifically Biosolver and Christian Lemon, for their help in building the spaces and get this project started. OpenEye for the support in developing the cloud-based FastROCS platform, and all of you for your attention. Thank you. And back to Christian.
Yes, thanks very much, Christoph. I hope you can hear me again now.